For large values of x, either positive or negative, the graph of the polynomial f of x equals a sub n x to the n plus etc., all the way down to a naught, resembles y equals a to the n, a sub n times x to the n power. So what this is saying is the ends of the graph. So for example, if you were to graph this function on your calculator, the middle of the graph could be all kinds of things, but the ends of the graph are going to look exactly like this graph here. Okay? So, once again, I didn't give you the graph, so let me draw them in. So let's take a look at these four graphs. There are certain things that you can kind of do in your head. For example, if you were to plug in 0 for x, you would end up with -6, right? If you plug in 0 for each of these terms, y equals -6. That means the y-intercept is -6. So 3 out of 4 of these have a negative y-intercept. This one has a negative y-intercept, this one has a negative y-intercept, this one does too. But this one has a positive y-intercept. So already we know it can't be this one. Here, let me label these A, B, C, and D. Let me change colors. Let's use purple. Okay, so already we know it can't be that one because it has a positive y-intercept. Okay? Now write that down. Positive y-intercept. Okay. We don't currently have any methods for finding the x-intercepts in terms of factoring this. So let's move on to investigate the turning points of each graph. Since f is of degree 4, the graph of f has at most 3 turning points. So let's take a look. This one has 1, 2, 3 turning points. This one has 1, 2, 3, 4, 5. So it can't be C, okay? Because it has 5 turning points. Okay? This one also has 1, 2, 3. So now we're down to B or D. Let's look at the end behavior. For large values of x, the graph will have to look like the graph of y equals x to the 4th power. Now, hopefully you guys kind of have an idea. The graph of x to the 4th power looks something, goodness gracious here. There we go. It looks kind of like a parabola, but it's more box shaped. So it's kind of like this. Okay? But it goes to infinity. F of x, as x goes to negative infinity, as x goes to positive infinity, the graph goes to infinity. This one has similar end behavior. This one resembles negative x to the 4th power. Okay? So it can't be this one. Okay? And I'll write a note here for end behavior. Okay? All right. Okay, graphing the polynomial function. Let me write this in. The degree of the polynomial is going to be the highest power. So in this case, goodness. You know what? This does not look right. This is what it should say. Go ahead and cross this out. It should say a sub n x to the n power plus a sub n minus 1 x to the n minus 1 power. Sorry about that. You guys can go ahead and change that. Alright, so the degree of this is going to be the highest power, so in this case n. The maximum number of turning points is going to be n minus 1, as we discussed earlier. When there's an even multiplicity, the graph touches the x-axis. When there's an odd multiplicity, the graph crosses the x-axis. Okay? Between zeros, the graph of f is either above or below. Oops. And the end behavior it behaves like y equals a sub n x to the n power. Alright? So, if we were going to analyze the graph of a polynomial function, there are 8 things that we can do. Alright, for these examples, this is the method that we're going to follow. We're first going to look for end behavior, then x and y intercepts, then zeros and multiplicity to see if it crosses or touches. After we do all that, then we're going to graph it on a graphing calculator. Or, and I know some of you guys have stuff on your iPhones and whatever, some graphing utility. Then looking at the graphs, we're going to look for turning points, graph it by hand, so it should have more detail. And then from our graph, we can determine the domain and range and where it's increasing and decreasing. Alright, so let's do it. Analyze the graph of the polynomial function, blah, blah, blah. Alright, so first thing, let's take a look at the end behavior. I trust you guys all know how to FOIL, so I'll just tell you what this FOILs out to be. Okay? If you FOIL this out, you end up with 2x cubed minus 11x squared plus 12x plus 9. Okay, so the end behavior we know is going to look an awful lot like y equals 2x cubed. Now hopefully you guys know that the graph of a graph of x cubed looks something like this. Okay, so we know as x approaches infinity, the graph is going to approach infinity. As x approaches negative infinity, the graph is going to approach negative infinity. Alright? Actually, I could leave that there. Alright, draw a little smaller. Something like that. Okay. So, after end behavior, we're going to look for the x and y intercepts. If we plug in 0 for x, we're going to get y equals 9. So we know the graph hits at 0, 9. Okay? Now, in order to solve for x, I'm going to go back to its factored form. If I set this equal to 0, I'm going to get x equals negative 1/2 and x equals positive 3 twice. So the other intercepts are going to be negative 1/2 0 and 3 0. Okay? So the multiplicity, this one is an even multiplicity, and this one is an odd multiplicity. So this one is going to just touch, and this one is going to cross. Okay? So now that we know all these things, I'm going to graph it on a graphing calculator. Alright, so I've got 2x to the third power minus 11x squared plus 12x plus 9. Okay, we graph it. Looks something like that. Alright, so I'm going to zoom out just a little bit. Let's go from negative 15 to positive 15. Oops. Okay, there we go. There. Okay, so we know it looks something like that. change colors. Use red. We know it hits at 9, so 1, 2, 3, 4, 5, 6, 7, 8, 9. We know it hits at negative 1/2. It's like here. We know it hits at 3. This one it crosses, this one it just touches. So something like that. Something like that. Alright, let's take a look at the graph and how different it looks than mine. So this is what it looks like. I did my best to draw it over here. Okay? So from this, we can approximate the turning points of the graph. It turns here and here. It's actually pretty easy to see where the turning points are. That's pretty much it. We don't really need to, whoops, turned off. We don't really need to do anything else because it's very easy to see where the turning points are. It turns up here and it turns down here. Okay. The domain and range, let me change colors again. The domain, hopefully you guys can see, it just keeps going on this way, it keeps going on this way. So all real numbers. In interval notation, that's negative infinity to positive infinity. And the range, it goes up and down forever. So, same thing. Negative infinity to positive infinity. Okay? Increasing and decreasing. It's increasing from negative infinity to 0. And then from 3 to infinity. It is decreasing from 0 to 3. Alright, so you guys can try this one, do steps 1 through 8. I gave you plenty of room. Okay, using a graphing utility to graph a polynomial function. Actually, you know what? I'm going to skip the rest of this notes. I think I'd like you guys just to skip with the first 8 steps that we learned. Okay? And go ahead and forget these 2 examples. So you can tear this page out or whatever. Or if you need more room for scratch paper, you can use it. Alright, and we'll do 4.2 in the next video.